So let's talk about W types today. First off, why is there a W in the name? Well, it comes from set theory. In set theory, you have something that's called a well-founded relation. I don't want to get into the precise definition. It's not that it's complicated, it's just I can easily get sidetracked. And yeah, the only important thing to know about well-founded relations is that they are it is what underlies every kind of recursion there is. Like, it underlies the usual recursion on natural numbers, it underlies structural recursion, it underlies transfinite recursion, stuff like that. It's really cool. It's really interesting. I definitely recommend that if you don't know what well-founded relations are, you check it out. I think there is a good article on Wikipedia actually about this. So yeah, I definitely recommend that you check it out. But this is where the W comes from, and the fact that it underlies recursion is what will motivate us to try and encode this or represent this into type theory. Because, you know, type theory works with recursion a lot. And if we want to study more generally types which are fundamentally recursive, such as natural numbers, lists, and stuff like that, then it helps to have a unifying framework, or in other words, it helps if we have a type that can encode all these other ones so that we can study just W types, and then we have results about all the other possible types that we can realize as W types, right? So I hope this makes sense. So I have paint here because W types are actually realized as trees, because trees are like the most fundamental recursion model. I expect that you know what trees are in mathematics and computer science, but if you don't, let's just say fast and loose, a tree is basically a system of nodes, and each node has a certain amount of children. It could be 0, it could be 42, it could be really any amount of children, and each child is itself a tree. And this is why it's the most fundamental recursive data structure, because it has nothing except recursion in it. There is no data. I mean, of course, most of the time people actually attach data to every node in the tree to use it. But if we want to get theoretical and just study trees for the recursive aspect, then we don't really have data attached to nodes. So we have some kind of data, because each node, which I draw as a circle, each node has a label. So for instance, this one is labeled A, and let's say that A has 3 children. Okay, so, and like I said, every child is itself a tree, and every tree starts with a root node. So we put the root node here. These are subroot nodes. Like A here is the actual root of the tree we are building, but each child is itself a tree, so it needs a root node. And maybe this root here is called A as well. Well, it's labeled A. And an important point is that the amount of children every node has is completely determined by its label. So this one is forced to have 3 children as well. And each child is a tree. But we can have as many labels as we want. So let's say this one is labeled B, and let's say every node that has label B will have one child. Okay, so maybe this one has label A again, and because it's labeled A, it needs to have 3 children. And I will finish my drawing here. Well, I will finish drawing the tree, but an important thing is that we want to realize this as... Okay, my face is in the way, sorry about that. Let me try to fix this. Okay, there we go. So we want to realize trees, because W types and trees are basically the same thing. We want to realize trees as types in type theory. And as you know, in type theory, everything is a type. This is a fundamental, like, primitive concept is a type. So the labels are going to be terms of a type, which we will call the type of labels. But we also need a second type, and this is not really a type, it's actually a type family over the labels. And this one will give us, like, for, let's call it C for children. For every label that you feed into it, it will give you a type that will encode how many children there are under this label. So this one is 3, the type with 3 elements and not one more. This one is CA as well. In my drawing, you see that C evaluated at B must be the unit type, because every node labeled by B has only one child, and so on and so forth. So given the data of labels, like a type for labels and a type family for the children, this specifies enough of the tree for the purposes that interest us, which are theoretical study of recursion. So enough yapping about this. Let's just jump into the code. We will try to use this picture description I made to actually encode some stuff in Lean. Now the fun begins. So let's call the type W, because we're talking about W types. And as I said, we need 2 ingredients. The first one is the type of label, type of labels. Oops. And the second ingredient we need is a type family that I called C, which is type family over the labels, which produces types. Now there is only one fundamental way of building trees, and that is using a root node. So we will call this constructor, this unique constructor, sup for supremum. If you don't understand why it's called supremum, I suggest you think about it, because it's really interesting. And the supremum will take, well, we're trying to build a tree via its root node, so we need to give, first off, the label that should go into the root node, right? But then that is not enough, because for every child under this root node labeled by A, we need to put 1 tree for each child, right? So how to say this in type theory? Well, this is a for each. So okay, there is a function there which takes some index, so some term in CA, and produces a tree again. And these 2 parameters here are enough to produce a term like that. Okay, so like I mentioned, this right here is can encode many different recursive types. In fact, anytime you have some inductive type that is fundamentally recursive, it can be encoded via W types. Right? So the most obvious example that comes to my mind right now is natural numbers. So you're probably sick and tired of the usual definition of natural numbers using like two constructors. So we can do it using W types instead. It's not going to be that different from the usual definition, but maybe it's be of interest to you. So let me switch to the paint scene here, and let me just remind myself to not forget to switch to the code scene before I start talking about code again. Okay, so how can we represent natural numbers as trees? Well, very simply. So we will have two kinds of nodes, which will correspond to the fact we have usually two constructors when we are building natural numbers. We have the zero constructor, which will correspond to a node with label 0, and this node, it has no children, right? We need to start somewhere. And then we have the successor node, or nodes labeled with S, which each have one child. And of course, this child is the predecessor. Okay, so here we have a construction at W type that represents, well, it's a construction that represents the number 2. So this whole thing here is 2. I hope you see why. But inside this construction, we have sub-constructions like this one. This represents the number 1. And this sub-construction here represents the number 0, of course. Okay, let me switch to the code scene now. So in order to represent this, we will define W0 as some W type. Let me open this namespace because I know from experience this will come to bite us. Okay, so we need to feed two ingredients before we can build this type. The first one are the labels. So let's call this type L. It's going to have two elements because we have two kinds of nodes. We have nodes labeled with Z or Z, and here I'll call it 0. And we have nodes labeled with S, and here I'll call it suck. Okay, so this is the first ingredient. We can feed it into this formation rule here. The second ingredient we need is the type family that will specify for each node type, I should say for each node kind, how many children it has. So let's call it C as well. And yeah, we can define it using pattern matching. So every time we get a label of type 0, we don't need to provide any parameters. So the 0 constructor has no parameters, or said in other terms, the node label 0 has no children. And yeah, the node label with S, or the node label with the successor, has exactly one child, so it is parameterized by the unit type, which has only one element. So we give it that, and there we go. We have actually here a definition of natural numbers, which are equivalent to the usual one, which I will leave to you as an exercise to prove. But it's interesting, like, what is 0 in this encoding? So 0 is going to be defined using the supremum constructor. So which label should we give it? Well, of course, we use the 0 label. Now we need to provide a function here. And if you look at what this function should be, it should be a function from C evaluated at the label 0 into some type. well, the W type in question here. This is actually not. So the thing to notice is C evaluated at 0 is actually the empty type, right? Like I can specify explicitly what the type of this should be, and it's going to be the empty type into W naught. And this type checks because everything is equal by definition. However, there is always one unique function from the empty type. It's given by the principle of explosion, or principle of explosion. I think that's the right term. We can build this function using the introduction of the empty type. I think it's called like that. Oops, it's not. Let me just look on the internet because I don't remember. Oh yeah, no, it's called lm. Yeah, of course, right. No, it's not intro at all because there is no introduction for the empty type, but there is one elimination rule, and the elimination rule will give you the unique function from 0 into any type. So, okay. This corresponds. We put this here because the 0 node takes no parameters at all. And what should be its successor? Let's say it's a function that takes a W naught and produces a new one. This can also be defined using the supremum. Of course, the label we want is this. And now, to produce the child of the node, what we want here is a function. Oops, what did I do? Oh yeah, okay, that's right, as a function. So it takes something like that, and yeah, it works better. Now what we need here, as you can see, is a function that goes from this, and if you recall this here, like C evaluated on this label is the unit type, so I can write it like that, and then so okay, this right here, like any function from the unit type into something, is basically just the choice of something here, of course. So what we can do is write a function that will ignore its argument and produce something of type W naught, and that something is going, of course, to be n. Let me remove this, because this is the successor constructor, and we give it n as an argument. This is basically it. Not really complicated. So we have 0, we have the successor, and using that we can build an equivalence between this natural number type defined as a W type and the usual definition. Okay, so I hope this makes sense. Let me see how much time do... Okay. I've been speaking for almost 19 minutes. So yeah, I'm not going to be speaking much longer, I think. I'm pretty tired. Let's see something fun. Let's see how the list, like how lists of integers can be, or lists of natural numbers can be encoded as W types, right? So the weird thing about lists is that you may think, like, if you know some inductive definitions of lists, my list of natural numbers, you may have seen a definition like that. So okay, a list is either an empty list, or something is not working here. Let's put int. Oh man, what am I doing? I don't need this. Okay, so A list is either an empty list or it is a list that has been obtained by appending something to its head. So it's usually called const for historical reasons. It takes something to put at the start of the list. It puts some old list. It produces some new list that has this parameter appended to the front. So this is the usual way that one will define a list. So you would think that just like we did for natural numbers, if we try to encode this as a W type, then we would have only two labels, like two nodes. But thing to notice here is this parameter here, which is not a parameter of type myList. So this means we cannot do it like that. What we need to do is take this parameter and kind of realize it or internalize it. What I mean is, instead of having const like that, we want to have const 0, which will add 0 at the start of the list. We want to have const 1, which will add 1 at the start of the list, and const 2, which will add 2 at the start of the list, etc. So, as you can see, we need to have an infinite number of constructors if we want each parameter to be myList. Like if you want to represent something as a W type, you cannot afford to have some constructor that has some parameter which is not recursive. They're kind of weird, but yeah, you need, in this case, we would need to have an infinite amount of constructors here. This is not a problem. This is not a problem because we can, let's say, okay, let me first put this into a namespace. Okay. So we can introduce labels. And how many labels do we have? Well, there is one label for every natural number, plus a label for the empty type. Sorry, the empty node, let's say. So what we can do is use a sum of types. So we would say the label may be defined as the unit type. How can I write this? No. I don't remember. So I want to write this. I just copy pasted it because yeah, so every natural number will be a label for a node, and then we have this special label which will represent the empty type. So we have actually an infinite amount of kinds of labels we can use. Now we need this function, this type family, over our labels. And yeah, let's do some pattern matching again, just to simplify our lives. So it could be of this form. I think, yeah. I'll do it like that. And then, okay, so if we are in this case, that means that the label in question is the one for the empty. So this is the empty label, so we have the empty type as a, like, there are no children. if we have a natural number as a label, then we have only one parameter, as you can see here. So we can ignore this as well. I will just delete this. Okay. And using this type of labels and this type family that encodes how many children every label has, we may say, okay, we have the type W list defined as this W type here. And now, this is also a cool exercise that you can do to show that this type right here, W list, is actually an equivalent type to the usual definition we may generally use for lists. So how can we encode the usual empty constructor? Well, as we did with the natural numbers, we can say W empty. This is supposed to be the empty list. So we will give it the empty label. The empty label is basically like, it doesn't matter what we put here. I just want to put it in the left slot and use unit point control. Okay, it doesn't work. So I'm getting really tired. Because I don't remember how it's called. Oh yeah, I'm dumb. So it's just the empty tuple. So we just need to feed, like, yeah, feed the only term of type unit to the left here, and then what do we give as an argument? Well, there are no arguments, so we do just as what we did for natural numbers, and use this, and this would be like, this would encode the empty list. Now we may do the same for the cons constructor, which takes usually a natural number, some list, and produces a longer list, right? Okay. Let's define it as a function. Take some natural number, and yeah, it does something with it. And this something is it takes also an old list. Now we may use the supremum, put some stuff to the right, and we use this, right? Because we're saying here, okay, use the label number n, and it takes one argument. So what this argument should be? What should this argument be? I should say. Well, okay, as before, when we have a function from a unit type, we don't really care about its argument. We just need to produce a list, and this one is just old list, of course. And this, my friends, is the append to the head function encoded as a W type, which is quite cool. Yeah. So before I end this video and go to sleep, I just wanted to say a little something about why this may be useful and why this encodes recursion. So let's go back to Paint. So the idea here is, suppose you want to prove that something is true for every term in the W type. Every term in your type, right? You want to prove it's true. Well, okay, not necessarily you want to prove something is true, but maybe you want to construct something. Okay, this if you want to construct a proof, then you are basically doing proof by induction, while if you're building some more complicated object than a proof, then you are doing definition by recursion. But the idea is this. So suppose we have constructed our object for every child, and suppose moreover that we have a way, given this, to lift this construction for the children, to lift it to a construction for the parent node or the supremum of the children. Well, you can use this to just build up and prove it for any root node that you want, right? So this means you have basically proven, or you have basically constructed whatever you're trying to construct for every element in your type, in the W type, using this idea of stages. So you have the base stage or the base case, and then you also have a way to go up one level, right? And this is why everything in recursion is a tree. Like here in the natural numbers, suppose you have your construction, you did it for 0, and you also know that it's always possible to lift this construction to a higher floor. Well, then the induction principle or the recursion principle tells you that you actually have defined this construction for every natural number. Well, it's exactly the same idea here. So, okay. I hope this was interesting, and I would really like to hear what you think in the comments if you happen to have watched this video up to now. And also I reiterate that I am a noob at Emacs, so if you happen to know a lot about Emacs, I would be really interested in knowing tips and tricks. Like I cannot figure out how to have completion. I know this. I could just Google it, but where's the fun in that? Instead of Googling it, I'm asking some random people that will maybe watch my videos. That's way fun. Anyways, I hope you liked it, and I will see you next time. I don't know what I will talk about next time, but I was thinking about maybe, like, one of my friends mentioned to me a book, about logic. It's a basic book, but it's really interesting and well written, and many proofs in it use recursion, but it's all based on set theory. But I think it would be interesting to make like some kind of course or like learning path for type theory, but using this book as a backbone. So yeah, tell me if you are interested in something like that, and maybe I'll do my next video about this. So see you next time, and have a great rest of your day. Bye.